Hi, in this video, we want to take a look at a confirmatory factor analysis, but we're going to look at some more advanced models than in the previous video. Okay, so first thing about factor analysis is that we believe that there are under the hood unobserved variables and we want to know more about these variables. So for example, let's talk about intelligence. So I can give someone a test and that test will tell me how well they did on those questions, right? And I can give them a test on another subject, another subject, and another subject. Okay, well, like all of these kind of like correspond with this idea of intelligence, but none of the tests actually tell us directly about intelligence. What they're doing, they tell us about how the person did on these individual tests. And what we want to do here is we want to use the data that we have that is observed to understand a variable that we can't directly get at, right? So we call the variables that we can't get at factors, and we call the variables that we observe indicators. Okay. Now, this example is coming from Modern Psychometrics with R, and here's the GitHub address for where I got the code, and I've modified the code quite a bit. Now, in exploratory factor analysis, we don't really know exactly what are the under the hood variables. All right. And in exploratory factor analysis, we're trying to figure out what those are, what it looks like, what is going on. With confirmatory factor analysis, I already have a model of these latent variables. And what I'm doing, I'm taking data that I have, I'm taking a model I already have, I'm putting them together, and I'm trying to see how well does my data fit the model? How well does the model fit my data? Because if there's a good agreement, then that confirms, that I have a good factor analysis model. If things don't work out very well, then I go, maybe I have a bad model, or there might be an issue with the data, but we would dig in deeper into that. All right, so when we do exploratory factor analysis, correlation is a big deal. But in confirmatory, nope. We don't even touch it. We don't look at it. We don't really care because we already have the model. And it's okay for factors to be correlated or uncorrelated in confirmatory factor analysis. We really don't care. Now, in the Levon package, so that stands for latent variable analysis. In this package, it has a special format for the formulas. If we see an equal sign tilde, that means is manifested by. If I see a single tilde by itself, that's a regression with the dependent variable on the left and independent variables on the right. And then if I see double tilde, then that means we're talking about residual covariance. All right, so when we talk about confirmatory factor analysis, there's some things we need to include. And these are standards that have already been established in the literature. So what we want first and foremost is a non-significant chi-square test. Okay, so why do I say non-significant? All right, so here we are doing like a lack of fit test. And so if we have a small p-value, that means that there is a lack of fit. If the p-value is greater than a certain threshold, then we conclude that there is not a lack of fit. So for the chi-square test, we're going to give the statistic, the degrees of freedom, all right, and then the p-value. That's everything you need for a chi-square hypothesis test using the chi-square distribution. Now, some things to think about with this. First and foremost, this is going to be a ward test, which means that if I have a large data size, then it's virtually guaranteed to be statistically significant. All right, so if I just have a lot of data, I'm going to reject the null hypothesis, really based off of the structure of what's going on, not based off of what's actually what's happening in the data. So if I have moderate to large data, I don't really sweat it being statistically significant. Now, if I have a low sample size, the power of this test is going to be relatively weak. So once again, I'm really not going to worry too much about it because I'm going to be prone to be making an error whether I like it or not. Now, we can take the comparative fit index, and we want that to be greater than 0.95. When we look at the root mean squared error, 90% confidence interval, we want the root mean squared error average to be less than or equal to 0.05, and we want its upper bound to be less than or equal to 0.1. Now, one of the reasons why this works out this way for these particular numbers is that we do a centering scaling on our data almost always before we actually do factor analysis. And we want a standardized root mean squared residual should be less than or equal to 0.08. All right, so when we're doing confirmatory factor analysis and structure equation models, we want to have at least 2 indicators per factor. All right, we want to have more indicators going into a factor than actual factors itself. We don't want indicator factor like 1-to-1. That really does not make sense, because if it's 1-to-1, if I have one indicator going into a factor, then the factor isn't a hidden variable, so it doesn't make sense to even do that. So we want at least 2 indicators per factor, and that just makes things like coherent and mathematically identifiable. Now, the more variables we have going in, more indicators going into a factor we have, the better. So two might be fine depending on the situation. 3 is better, 4 is best. More than 4, we're going to be like really, really happy. All right, so now let's take a look at multi-group confirmatory factor analysis. All right, so what we want to do, we want to extend factor analysis to testing parameters differences across groups. So I want to test parameters across different groups, similar to how we do this with a t-test or an ANOVA test, but now it's on latent variables. All right, now when we do this, we want to consider including an intercept in my model when we're computing the means of latent variables. All right, there's 3 invariances that are really important for this. There's configural invariances, which is unrestricted loadings and intercepts across groups. Weak invariance, the factor loadings are constrained to be equal across groups. The intercepts are free. And then we have strong invariance. The factor loadings and indicator intercepts are restricted to be equal across groups. All right, so we can see that there's kind of like an order to these. All right, so let's go ahead and take a data set from Modern Psychometrics with R's package. And we're going to take the prejudice data set. And here we have a data set, a data frame with 861 individuals and 10 scores. What we're going to do, we're going to take a look at these measurements of prejudice and then run our confirmatory factor analysis. We're going to believe that, so our belief right now is that these 4 are contributing to like a global aspect of prejudice. And we have a model that we will run with for this. So let's go ahead and load the data. So the data set is Berg, because that's the author of the paper who volunteered to donate it. And then here's the package we're getting it from. And I go ahead and I sort things because of the upcoming visualization. I want something to be easier to see in a second. And then here I'm going to run a pairs command just so I can get a better idea of the variables that I'm working with. All right, so when I was looking at this pairs plot before I made the video, I noticed that the HP, so HP is sexual prejudice against gays and lesbians. I noticed that there's like 2 distinct groups here. And I was like, what's going on with this? I'm interested. What is causing this split? Don't really know. I'm sure if I read the paper, I could dig into it more. But for our purpose right now, I just want to kind of dig in just a little bit deeper. And so what I did, I went ahead and I plotted these points in this group, green, across all these plots. And so I can kind of see that they're where they're distributed. And here, I don't really see a whole lot of difference, like, between the green and the blue. There are more green over here, but with this plotting technique, it's hard to tell if there's something else a little bit deeper going on. And so there is a bit of a concentration, but I can't tell if the blue is more concentrated here also. Okay, so we want to do measurement equivalence confirmatory factor analysis. So we're going to be using the mes equal syntax function from SimTools. And what we're going to do, we're going to use this model for us. So there is like a global prejudice factor. And these connect, our indicators for them are our 4 prejudice data columns. Okay, so now when I do multiple group analysis, we can evaluate equivalence across these values. So we've got loadings, composite loadings, intercepts, means, thresholds, regressions, residuals, residual covariances, LV variances, and LV covariances. Okay, so we have plenty of options with this. Okay, and we're going to put these into the group.equals parameter of our modeling. So what we're going to do at this point, we're going to run models with different group equal parameters, and then we're going to compare them and see which one looks like it's going to be the best one to work with. Okay, so group equals, and here I'm taking the default null one. So I'm not putting any restrictions on equality of the variances. When I do this one, you notice I don't have the group.equal parameter present in this command call. Now here, I'm going to go ahead, I'm going to say that I want loadings to be equal across groups. Oh, and my group is gender. Now on this model, I'm going to go loadings and intercepts. So I'm tacking on intercepts onto the previous model that we created. And now I'm on this model, I'm going to tack on means for equality across groups onto the previous model. All right, so you'll notice that it's like I have, a nested aspect to the modeling, which means I can run additional hypothesis tests to evaluate or to compare these models. So let's run ANOVA. So what I'm going to do, I'm going to take all of these models. I'm going to take the one that didn't have any variance equal groups requirements. Then I'm going to take where the loadings has to have equal variance across groups. Then loadings and intercepts, and then loadings, intercepts, and means. So this one will be the most restrictive of all of them. This one's the least restrictive. We're going to do a chi-square test. And so here, this is the part we really want to focus on. All right, so we have, we see that we have statistically significant, statistically significant, statistically significant. All right, what does this mean? All right, well, each time I have, statistically, I have really different models. Okay, they're not, they're not equally informative to each other. And I look here, statistically significance means that the model with more equal groupings is actually worse than this predecessor. So what we're saying is that the one with intercepts, this hypothesis test here tells us that intercepts is better, or loading and intercepts is better than the loading, intercepts, and means. This hypothesis test says that the one with just loadings is better than loadings and intercepts. And then this hypothesis test says the one without any restrictions is better than the one with just loadings. So the best model for this output is actually the one that is using the default aspect where I have flexibility across my models. All right, so let's go ahead and take a look. So we're going to take the one that did not have any restrictions on the variances across groups. And we can see the number of free parameters, number of males and females in each group. All right, so we have a class imbalance here, but that shouldn't be too much of an issue here for this problem, but be something to be mindful of maybe down the road. Here's our test statistic, our degrees of freedom. Now this is just testing on the null model only, it's not comparing. Here's our p-value, which is not statistically significant. And here is the test statistic for each group. All right, so now we want to take a look at multi-group confirmatory factor analysis, but this time, instead of like having different models that we're comparing, we want to run hypothesis testing. All right, so in this situation, the Levon package gives us two ways to declare how we're going to approach this. We can explicitly incorporate the loading restrictions in the model formula. I'm going to call it the vector version because you have a vector multiplying your indicator variable in the formula. And the other way is to use the equal across groups parameter to specify what's going on. All right, so let's take a look at the vector version first, the one that's this version. All right, so if I look here, you'll notice that I've got two groups, right? I have two groups, and I'm saying I've got V1, V2, so I'm saying these are going to be the same as each other, and it's going to be male and female. So remember, male is first in how the factor is set up. So this is male, female, male, female, male, female, and I'm specifying that we have to have equal variances with respect to each of these indicators. Now you notice I don't put anything on the SP. All right, so that's a little bit different. Now, when I go down to the second model, and here these are the models that the author of the textbook are using. Same thing as before, same thing as before, same thing as before, but we have NA and 0. Okay, so what's happening here is that for females, the parameter is being set manually to 0. This one is being allowed to be whatever it is. So the one on males can be anything. The parameter on females has to be set locked into 0. And now when I get down to this version, so I want to restrict loadings across groups using the group.equal argument, I can get to here, and on this model, we want loadings to be equal across groups. In this one, we want loadings and intercepts. And we want loadings and intercepts on this one. The difference is that now, if I compare these two, we can see that the global is being manifested by SP. Okay, so now let's take a look at these. We want to compare them. So I'm going to run ANOVA on all of them to see what happens. Okay. Well, when I do this, I get a bunch of warnings. So I'm running ANOVA on the 2 vector versions and the 3 groups.equal versions. Get warning, warning. And then I look here and go, hey, well, what's going on here? I don't get any p-values. The reason for that is because the model structures are not comparable to each other. So here, this p-value corresponds to 2 models that are comparable, but that's it. The rest of them, sequentially, I do not have comparability. So let's go ahead and run ANOVA on comparable models. So let's do vector loading 1, vector loading 2. If I look up here, I can see that the difference is there's nothing multiplying SP, while here I have that restriction. And we have group equals and group partial being added to the second one. See what happens. And here we see statistical significance. So the one that is less restrictive is the one that we would prefer to use between these two. Now, if I want to compare vector loadings 1 with the third model that we built up, these are not comparable to each other. Now, if we do model 1 with vector loadings 2, we see that it's statistically significant. So we want the simpler one. And when I compare these two, they're not comparable to each other. And when we go with these two, they're not comparable. And when I look at these two together, model 2 with model 3, we have statistical significance, so we would want the simpler one. All right, so now let's take a look at longitudinal confirmatory factor analysis. All right, in this situation, we have longitudinal data. And what I want to do, I want to be able to use it, right? I mean, does that make sense? Like, how many times do we have time series going on in anything? Well, let's go ahead and pull that in. Let's take advantage of it and use it. All right, so for this one, we're going to use a social dominance orientation. It contains 4 social dominance orientation items measured across several years on a 7-point scale. And there are 2 overall types of, our confirmatory factor analysis is for 2 types of factors, or 2 factors, and we're splitting up the indicators. We have anti-egalitarianism, and we have dominance on this one. And here are the fields that we have to work with. All right, so in this situation, it's a little bit more complicated than what we looked at formula-wise before. So just to remind you, if I have equal sign tilde, this is saying manifested by. This is a latent variable dependent on observable variables. If I have a single tilde, this is a regression model where the dependent variable is on the left, independent variables are on the right. And here, when I see double tilde, this one's new for us, this is a residual variance covariance modeling. All right, so now let's go ahead and take a look. Now here, I'm going to use the years 1996 and 1998. And here are our formulas. So these are pretty standard for us at this point. All right, so here we're saying that we want to have a variance covariance residuals, variance covariance relationship here. And here we're going to be doing regression of these variables predicted by these over here. And now we're looking at residual covariances. And then we're going to be doing regression of to establish a baseline. And so here we're going to use the confirmatory factor analysis function. I'm putting in the model, I'm putting in the data. Once I have that, I'm going to want to get parameter estimates. And then I want to take a look at the confidence intervals that I've got going on to see, maybe I should remove something. Maybe I should keep everything. I don't know. Let's take a look. Let's see what the data says. Okay, so if you look at how the parameter estimates output comes in, it'll give us a data frame with one column will be the left-hand side of the equation. The next column will be the equal sign tilde or double tilde. And then the next one will be the right-hand side of the formula. Okay, so what I want to do, I want to plot confidence intervals using geom error bar from the ggplot2 package. So what I'm going to do, I'm going to paste the equations together. That way I have the left-hand side, the operator, and right-hand side in one column. And then I'm going to sort them by the estimated value so that I can sort it and make it easier for me to spot what's going on. So let's go ahead and do that. All right, so there's plenty of things going on here. There's a lot of stuff to look at. And I can see if I, crossing 0, all of these up here are not crossing 0, so these are looking good. Now over here, I have some concerns, and I would like to take a little bit closer of a look. So here I've got regression, and then we have the residual covariances. Let's go ahead and plot it to see what's going on, to give you visually a better idea of what's happening. And so here I can see that this is 0.8, and then this is about 3, a little bit of a gap in size. So if I was like rerunning this, I might want to consider dropping this. Once again, we have 0.8 and 3. Now let's do another model, but this time I'm going to incorporate 1999. Okay, so 1999, I have another year on there, which means I've got more stuff going on. So here, I'm doing latent variables depending on indicators. Now here's a second level. I'm doing the same thing, but you'll notice I have SDOD, which is on the left-hand side. Now it's on the right-hand side. To really wade through these formulas, you have to pay attention to the exact characters in there, because they're all like very similar. All right, so now we want to do regression here. So here we're going to have constant first level intercepts. Now we want to take a look at residual covariances. And now we want to take a look at Latin means using regression. And so that just sets up the formula. That doesn't actually do the confirmatory factor analysis. On this step, I'm running the confirmatory factor analysis. And so once again, I want to take a look at the confidence intervals. So let's go ahead and get the parameter estimates, which will give me the confidence intervals, but it's not quite in the format that I want for the purpose of ggplot. So I'm going to do exactly what I did before of getting the formula for each row into one column. And then I'm going to sort those rows, those formulas by the parameter estimates. That way it's easier for me to interpret what's going on with the confidence intervals. And so here, I've got 0 over here. So the ones that are up this way, I know that they're statistically significant. So if I'm going to remove something, I'm not going to be looking at these ones. I'm going to be looking down here. Like these ones are going to be a lot more interesting for me if I want to do backwards elimination to get a simpler factor analysis model. And let's go ahead and plot it to see visually what's going on. And so, you know, it looks kind of interesting. So we can see that we have the dominance. Yeah, these are the dominance factors, and these are the anti-egalitarian factors. And these are like our overall factors. And you can see that we have a connection between years in this manner. All right, now let's take a look at multi-level confirmatory factor analysis. All right, so for this situation, what we're going to do, we have a situation where we have data, a level of data that's nested inside of another column of data. So the situation is that we have some data that includes families and identifiers for members within each family. Okay, well, a family is a unit, and I've got individuals. So therefore, individuals within a family, children within a family, are nested within their family. And so for this nested structure, I need to do something a little bit different. I can't just go, so here the ID variables are 1, 2, 3 for the members of a family. Well, number 1 in family 1 is different than number 1 in family 2. So I have to tell R that I have a nested structure. If I don't tell R it's nested, things are going to get really wonky. Because it's going, if I don't tell it that way, it's going to assume member 1, that value in family 1, and the value 1 in family 2, and the value of 1 in family 3 are all like equivalent to each other, which is not what we want. And so here we have family, we have the child, and then we have measurements of intelligence. Okay, so first thing I'm going to do, once again, I'm going to load the data. Now, I want to visualize the data. I'm going to use a pairs plot in a moment, but I want the colors to kind of correspond to, want them to be more informative than just you putting black dots. I want more information coming out of this. So what I did, I decided that I'm going to do, first principal component analysis, and then I'm going to find the median principal component analysis value for each family, and then I'm going to use that value to color each family. So let's take a look at the output. So each member of a family has the same color circle dot in the pairs plot. So when I look at the darkest values, I know these all correspond to the same family. When I look at the lightest values, these all correspond to the same family. And you can definitely see that the colors overall as a trend increase as they go from dark to light as we go from left to right. So that just immediately shows me that there is something going on with this whole family thing in terms of intelligence. Now, what it is, to what extent, I don't know yet, but it's not a 100% guarantee aspect, because I can see that there's kind of like a dispersion of the dark values. Some of the dark values are going into the lighter region, and some of the lighter regions are going into the darker region. Okay, so it's not 100% like perfect correlation. I'm using correlation incorrectly, but it's not a perfect correlation between family and intelligence, but I can see that there is something going on just off of this plot right here. So let's go ahead and start digging deeper. Okay, so what we're going to do, we're going to say that level 1 is numeric and perception. So numeric is manifested by word lists, cards, and matrices. Perception is manifested by figures, animals, occupation. And then general is manifested by all of them. Now, another thing I could have done, I could have instead put numeric and perception here. There is a difference though. If I would have done numeric and perception, then there would not have been as much flexibility to fit. But that might be good, might be bad. For this situation, the author chose to have general depend directly or be manifested directly by the 6 indicator variables. And if you go both ways with this, you will get different results. And something that is important when I'm using the Levon package for this, you need to have the level 1, level 2. If you don't have these, it's going to assume a different model structure, and you will get different results. They won't even be comparable to each other. And so here we can see that we have a non-statistically significant p-value. Okay. So we do not have a lack of fit. And we can see that we've got 60 families going on, and we have just under 400 observations. All right, well, that's all I've got for you. Take care and goodbye.